Swayam Prabha. Digital India. Educated India.
Okay, so now so the second topic I want to talk about again is basics on crystalline defects. So Anand and Ilak told me that most of you will know that very well. So I was thinking of going rather quickly about it. But if you have questions or if you want me to slow down, don't hesitate. So for the crystallography, I didn't give any references because it's really a very typical topic. For overview of crystalline defects, not just overview, for crystalline defects, there's this very good book by Wei Tsai and Bill Nix that gives you a lot of information. And actually, I wanted to use their book cover as a matter of introduction and ask you, so they've decided. So this one this one is edited. So this one is me, but the others are from Wei Tsai's book. And I wanted to ask you, in these pictures here, what kind of defect do you see? Because basically, there's an illustration of every type of defect you can find in a crystal. So. Yeah, so these are point defects. What kind of point defects? What do you think if it's black, it's a vacancy, right? It's an atom. So a vacancy is an atom missing in the crystalline structure. So you have here examples of vacancies, yes? Then what else? What is? It's a grain boundary, yeah. And can someone be even more specific? Does someone recognizes what kind of grain boundary? So this is a grain boundary in the sense that I have a grain here, I have a grain there, and they don't have the same orientation. And there's a surface here in between those two grains, and it's called a grain boundary. Yeah, it's a symmetric tilt grain boundary, right? So if I look here, I have a symmetry between the two planes here. So this is a very simple and well-ordered grain boundary, okay? Now this, I'm not sure if it's clear, but maybe I should put the scale. So the scale here would be maybe 1 nanometer, maybe. So that would be. So no, actually, it's hard to know. It's voids. So usually we categorize the defects as punctual defects, vacancies and interstitials. So point-like defects. We have surface defects here with grain boundaries. We have volumic defects with voids and precipitates, for example. And what remains is here. So what is this? So what might help you is if I draw the planes around it. So if I draw planes of atoms, what I see is I have here 2 extra planes that end in the crystal. That's a dislocation. And that dislocation here would continue perpendicular to the plane, so that's a linear defect, right? So the 4 main classes of defects are point defects, vacancies, interstitials, line defects, so 1D defects, dislocations, and then also I'm going to say a little word about disclinations and disconnections. Then we have surface defects that can be grain boundaries, twin boundaries, stacking faults that we have already talked about. And then we have the volumic or volume defects, precipitates, and voids, right? So what I thought I would do is do a table like this, where we have the defects, and then we have how they are produced or annihilated, and what type of mechanism they are related to. So for example, if we say vacancies, so where do vacancies come from? So clearly irradiations would create vacancies, but without irradiations, are there vacancies if I take, I don't know, a metallic spoon? Are there vacancies in a spoon? Yeah, actually, so vacancies are, the energy to create a vacancy is low enough that I can have an equilibrium concentration of vacancies, non-zero equilibrium concentration. It's the only equilibrium defect. All the others we're going to talk about, at equilibrium, they don't exist. Only vacancies exist at equilibrium. So we have vacancies everywhere, yeah? And so what's the main source of vacancies for a metal? It's free surfaces. The free surfaces and the volume outside, this is an infinite source of of vacancy that can come inside to reach thermal equilibrium. So these are, yeah, they all appear at the same time. So, okay, so vacancies, they are created by, we said, just free surfaces, irradiations, and then there's a third mechanism. Maybe it's not, it's through plasticity, through jog drag. We can talk about that later on. But okay, what type of macroscopic mechanical mechanisms vacancies are related to? In what type of processes do vacancies play a role? They would create stresses, but that's clearly not their main their main action in a metal or in a crystal. Diffusion, right? So diffusion in most metals, in most systems, happen by an exchange between an atom and a vacancy. It moves, the atoms move around by exchanging with the vacancy. So their main effect is in diffusion. In plasticity, where do vacancies play a role? In what type of deformation do vacancies play a role? Creep. So deformation at high temperature will involve the either absorption or production of vacancies, right? Okay. I think there's another one, but yeah. And now interstitials. So how are interstitials created? So interstitials are extra atoms in the matrix. How are they created? So you have some interstitial solutes, so solutes that are small enough that they can find a position in between the atoms, yes. And then self-interstitials, or interstitials of the same nature as the matrix. When do we have interstitials? The oxygen, yeah, but so that would be an interstitial solute. But if I have a pure element, like, I don't know, pure copper, when do I see interstitials in pure copper? To my knowledge, there's only one case. It's irradiations. In normal life, in pure copper, there's no self-interstitials. To my knowledge, maybe I'm missing something and you can correct me. The only case where you can have self-interstitials is because of irradiations. It's the only process that has enough energy to create interstitials, because interstitials, one, they cost a lot of energy, self-interstitials. So they are really far from equilibrium defects, and also they move very fast. So they cost a lot of energy, and since they move very fast, they will very quickly reach either a free surface or a grain boundary. They will eliminate, and you won't see them, unless you have a steady production of irradiations, of defects, and that's through irradiations. So crystals have different densities, right? So in BCC, you have enough space to put an extra atom. In FCC, and we're going to see the example this afternoon, you're going to model an interstitial in FCC. In FCC, there's not enough space. As someone said earlier, the atom touch. And so the interstitials in FCC have a special structure, which we call a dumbbell, where it's one lattice site that is shared by two atoms. Instead of putting an extra atom here inside, what you do is, you take one atom, or one atomic position, and you put two atoms around it. Right? So that's 2 for 1. And that's called a dumbbell, like the thing you do at the gym, right? I'm not sure if there's 1 or 2 B's. Yeah, so yeah, this one is, so again, I usually take simple cubic as an example, but this is not, so a real crystal would be more like this, right? With atoms. And there's not enough, so you can put a small atom, so that would be an interstitial solute, like oxygen or hydrogen, for example, or carbon. Carbon is small enough that you can find carbon in between atoms. But for the self-interstitials in a normal system, there's not enough space. And that's, in particular in FCC, that's where you get these dumbbells. So 2 atoms that share one atomic. And even, I mean, the first nearest neighbor here will also be displaced a little bit. And then the one here also a little bit, and then less and less as we go away. So it's more like you have maybe 6 atoms that share 5 positions. Yeah, but in practice, when you look at the dumbbells, they are always oriented along a 110 direction. It costs, in the end, for the crystal, it costs less energy to orient that dumbbell along a 110 direction than along any other direction. Yes, and so that was for interstitials, and the mechanism which is related with interstitials. Yeah, there's not many, but there's irradiation hardening. Again, everything is related to irradiation when we have interstitials. So let's see if I've said everything. So sources, we said free surfaces, jog drag, irradiations, and then vacancies can cluster also. They don't necessarily remain isolated. They can cluster to form either cavities if you have many vacancies, but also they can form dislocation loops and a special structure in FCC which is called a stacking fault tetrahedron. We don't need to go into the details. Interstitials, they are high energy irradiations and they also form clusters in the form of, in particular, dislocation loops. And then here we have diffusion and creep, and here we have irradiation hardening. In terms of punctual defects, there are 2 other types of defects. So one which you also find in metals that are Frankel pairs. So Frankel pairs is it's a pair. It's a combined. It's 2 close by vacancy and interstitial. It's a pair of a vacancy and a close by interstitial. I'm not sure there's one. Yeah, it would be here. So I have a vacancy and nearby I have an interstitial. So that would be called a Frankel pair. This is a type of defect which is created by low energy irradiations, like electron irradiations typically would create Frankel pairs like this. Yeah, it accelerates. All the diffusive phenomena are accelerated under irradiations. So I won't talk about it, but you have a concept of an effective temperature. So when you have constant irradiations, you can define, in simple models, you can define an effective temperature, which is higher than the real temperature, and that will depend on the flux of irradiations. You can also have non-equilibrium phases induced by these, since the diffusion is faster, you can also stabilize through diffusion, you can stabilize phases that would not be stable at that temperature. Yeah, and then the other example, and this is in non-metallic systems, you can have these Schottky pairs, which is, it's like a Frankel pair, but with an ionic crystal. So you can have, if you take an ion and you move it, you will have a charged vacancy and a charged ion next to it. And that's called a Schottky pair. Okay, now dislocations. I'm not sure I want to go too much into the details right now of what a dislocation is, because that could take hours. It's a line defect, and in the simplest case, as we saw in the example, it's an extra half plane. So how many of you do not know at all what a dislocation is? Just a show of hand. You all know what a dislocation is? Oh, yes, that makes my life. You don't. Sorry, man. Okay, bear with us. There'll be a special lecture on dislocation. So for today, I'm going to talk about mostly to those who know what a dislocation is. How are they produced? So a dislocation, it's a line defect. And what is the main mechanism to which dislocations are related to? Yeah, plasticity, right? Dislocations are the main carrier of plastic deformation. How are they produced? They multiply during plastic deformation. Dislocations multiply through the very well-known Frank-Reed source that no one has ever known. There are a few people doing TEM who have seen one Frank-Reed source in their whole career. So they are very proud of seeing one. So that's the example that we all take to show how dislocations can multiply, even if in practice they do not multiply through Frank-Reed sources. They're extremely rare in practice, but they multiply through deformation, and so they're related to plastic deformation. And what type of so if they multiply, what will happen in the crystal as the dislocations multiply? So the dislocations will block each other, and so that will harden the crystal. And so the dislocations are related to strain hardening, right? So they are produced by plastic deformation, the Frank-Reed source. They are also involved in crystal growth, right? Many crystals, they grow around screw dislocation, for those who know what it is. So they're also involved in crystal growth. And they are non-equilibrium defects, so if you heat at high temperature, they will annihilate. Main carrier of plastic deformation, they control the plastic yield through, for example, the Taylor's law, and they're related to the strain hardening. So dislocations, as shown here, they adapt a localized shear in the structure, in the crystal. Now, there are other types of line defects. In particular, you have disclinations that they accommodate not a shear deformation, but they accommodate an opening. So for example, if I take a system which does not, which at equilibrium, I take a continuum material like this, which at equilibrium does not want to close, and I force it to close. So I put glue on both sides, and I glue them together. So I'm going to have a system which is like this, and with the angle that has been closed, the system is out of equilibrium, and the defect that allows this closing here is called a disclination. The typical example that we see often experimentally is what I call the penta twin. So if you take, so it's that takes me into a lot of details, but remember we talked about the FCC crystal, and we talked about this tetrahedron of the 111 planes. Now imagine I take one of these tetrahedron, then I glue on this face another tetrahedron. So that would be something that would look like this. Then I do it again. I do a third one. Then I do a fourth one. Then I do a fifth one, right? So I add tetrahedra one next to each other. When I'm back with 5, there's a small angle here that remains. So in a crystal, that angle here would close. And so I would form at the intersection of all of these tetrahedra, I would form a disclinations, an angular defect. Now, when I'm adding, so we're going to talk about that later on, but when I'm adding triangles like this, I'm taking twins. So I have one crystal here is twinned with respect to this one, and this one is twinned with respect to this one twinned, etc., etc. So I have 5 twins, and to glue them together, I need an extra disclination. And this is what is shown here on this experimental example. You have here one FCC crystal. It's twin, again, twin, twin, twin. I have 5 of them. And then to glue them together in the middle here, I need a disclination. This is something that you see in nanowires. There's been a lot of studies on nanowires. And the last linear defect is when you have a grain boundary. So we're going to talk about grain boundaries after, but imagine I have a grain boundary. So if I take the example of earlier, I have a symmetric grain boundary between 2 crystals. And now on this grain boundary, if I have a step, in some cases, these steps can have a dislocation character. They can act like a dislocation, but it's a dislocation on a surface. So it's a 1D defect on a 2D defect. And this step here with a dislocation character is called a disconnection. You see them in particular when you're looking in HCP crystals at how twins move. You form these disconnections. So this is a defect on a defect, disclinations. This is an angular defect, and this is a displacement defect. Yes, that's enough for now for dislocations. Now the 2D defects. We have grain boundaries, and there are different types of grain boundaries. What do you think? What do you think are the different types of grain boundaries that we? Yes. So symmetrical, non-symmetrical. We have twist grain boundaries. We have tilt grain boundaries. But then inside the grain boundary, we can have low angle grain boundaries. And they are made of what? Or how can we model these low angle grain boundaries, for those who know? With an array of dislocations. And then we have the high angle grain boundaries. And then in the structure of the grain boundary itself, it can be ordered or disordered, right? So many types of grain boundaries. How are they produced? Yeah. So they can be formed if you first create single crystals and then you glue them together. That would be, what's the name of that process? Sintering, right? Sintering is when you take elementary grains and you glue them. I mean, yeah, you glue them together. So they would be formed by sintering or just by plastic deformation and accumulation of dislocations into grain boundaries. What type of mechanism are grain boundaries related to? Yeah, so dislocations will be very strong obstacles. No, sorry. Grain boundaries are very strong obstacles to dislocations. And what's the name of the related mechanism? Hole patch, right? The fact that the smaller the grains, the larger the yield strength, the yield stress, and that's called hole patch effect, right? So there's a hardening of the system through a decrease of the size of the grains on this side, and then they are formed just by solidification. If you have at different places in space grains that start to grow with different orientations, when they join, they form grain boundaries. So naturally through solidification, plastic deformation, sintering, and again, they are non-equilibrium defects, so they anneal at high temperature. Then we have twin boundaries that we have already talked about. Maybe I can hide it like this. So we've said, so we have twin boundaries. So they join two crystals that are related by a mirror symmetry. And so it's a specific type of grain boundaries. We have the stacking faults that we have already talked about. And then we have something that has come up in the research field not very long ago that are called complexions. Does anyone know what a complexion is? In the grain so inside the grain boundary here, because the bonds are far from equilibrium, you can actually stabilize phases that are not equilibrium phases. You can stabilize along a grain boundary. You can stabilize a phase that exists just because there is a grain boundary, and that's the complexion. There's quite a bit of activity in the materials research field to look at these complexions. So it's interfacial phases stabilized inside a grain boundary. The idea would be, can you use them to form metals that are both, as always, strong and ductile, for example. Yeah, that would be, I think, I'm not a specialist of complexions, but I think that would fall into the category of complexions. If the quasi-crystal is stabilized because there is a grain boundary, then it is a complexion. And then 3D defects, I'll go fast. So 3D defects, so same thing. So we have, the main 3D defects are precipitates, and they can be either completely coherent with the matrix, or they can be semi-coherent, where there are dislocations in the interface, or they can be completely incoherent with the matrix. They are formed through heat treatments, and they are related to precipitation hardening, right? I don't think I need to say much more about that. Do you have questions or not? I think I'm rushing a little bit because I would like to talk about atomistic simulation so that you can do the tutorial this afternoon. And I still have a lot of slides about atomistic simulations. Is that clear enough? Good. I'm going to go fast. It's just to give you a feel for what atomistic simulations are. And then we'll talk into much more details through the tutorials, okay? So I want to talk about three things. First, the typical length and time scales that we have in material science in general and in particular in simulations. Then I want to say a few words about energy models. I'm not going to go into any details, so I just want to say a few words about traditional potentials, and then really very quickly about machine learning potentials. I could spend the whole week talking about machine learning potentials. I don't want to do that. And then also a few words about atomistic methods, molecular statics, and dynamics. In doing so, I'm only going to talk about structural and thermodynamic properties, and through the week it's going to be like this. So we're not going to talk about functional properties that would require more advanced energy models. And okay, so I've already said that we're going to use lamps as an example. Now, the basic and most important ingredient of any of the atomistic simulations is the energy model. So what's the energy model? It's basically, it's a function that as an input takes an atomic configuration. And an atomic configuration is made of three things: atomic positions, the chemical nature, so atomic position, so the position of every atom in the system. Then we also need to know what is the chemical nature of each of these atoms. And then we also need to specify boundary conditions. So these three ingredients together, they form an atomic configuration. And then the energy model will tell me, for these atomic positions, these chemical natures, and these boundary conditions, what is the energy of the system. In these positions, for example, if you have a vacancy, you will have positions here at every atomic position in the crystal, except that there will be one atom missing. So the atom, the vacancy will be encoded in these atomic positions. Sure, yeah, that will come later, yeah. But vibrations are a result of energies, of interactions between atoms, and so vibrations are a result of it's coming from the energy. The most fundamental information that I can give for a system is its energy. And from that, you can get everything. So we'll talk about vibrations. Yeah, that's clear, yeah? So what would be the simplest energy model that you can take? So a Lennard-Jones potential, so what does it look like? Exactly, yeah. So if you want to, yeah, if you draw with your hands a Lennard-Jones potential, what it would look like? Yeah, it does this, right? So this is the most basic energy function that we can use to represent the interaction between two atoms. And then we sum these pairwise interactions to get the total energy. Before we talk about potentials, so the length scales. So we've already talked about the smallest length scale, which is basically the unit cell. And the size of a unit cell, it will depend on the system, but it's going to be, on the order of half a nanometer, roughly, right? So that would be the smallest length scale that we are interested in. And it contains one or a few atoms. Then the scale above is what I call the representative volume. So it's still a small system, typically between, say, 10 and 100 nanometers in size. It contains on the order of 1 to a few million atoms. And if you choose well this volume, you can put most of the physics that you want to study into this system containing a few million atoms. So representative volume for many processes. And then you can also go to the scale above. So that would be the grain scale. So the size would be, say, from 1 micron to 10 or more microns, where you put, you don't try to simplify your problem. You just run a big simulation and you look at what is happening. So that would be the grain scale, and the order of magnitude of atoms would be a billion to a few billion atoms. Now, with a laptop, a workstation, or a single node calculation, we can do this and that. Now, to do this, you need to be Vasily Bulatov and be at Lawrence Livermore National Lab and have access to some of the biggest American computers to run these simulations. So this is only for very, very big supercomputers. Together, we're going to do this and a small portion of that, because otherwise, even this would require several days of calculations. So 10 to 100 nanometers. How big is that? So I just took 2 examples. So this is from a in situ TEM experiment, and you see the scale here. This is 100 nanometers, and we said, basically here we are between 10 and 100. So this length here would, on the order, be the size of this bar here. And so, if I work well, I can put a full dislocation. So these are dislocation segments. And you can see that with 100 nanometers, I can put basically one dislocation inside. So I can study in realistic volume, one dislocation, not 2, right? Just one. But with one, I can have a realistic volume. If I look at a larger scale, like a grain scale here, this is 100 microns. This, the atomic scale, just forget about EBSD. but you can try to make a contact with in situ or TEM in general, in situ and high resolution TEM. In material science, there are two main types of processes. And again, we're going to have the good guys here and the bad guys there. Does any one of you has any idea of who could be the good guys and who could be the bad guys in the story? In terms of simulations, if I ask you, please simulate at the atomic scale, so using lamps, please simulate, I'm not going to say because I would give you the answer, please simulate some process. Yeah, so that would be part of it, but that would not be, the elastic constants would not be an issue, no. There are some processes, if I tell you, please simulate something, you might say, oh, I'm not going to be able to do it. So there are, equilibrium processes, yes. So that would be some of the good guys, but most of what we're interested in is out of equilibrium. So for example, in plasticity, if I say, please simulate the glide of a dislocation. So hardening would be hard because you need a lot of dislocations, but surface relaxations, that would be among the good guys. So high temperature, yeah, could help with the bad guys, but so for example, if I say, so I take two people, for example, you two, and I say, you please simulate a dislocation, an FCC dislocation, and you please simulate a screw dislocation in a BCC metal. One is lucky, the other one is not. Why is that? BCC is difficult, yes. Why is it difficult? Why is simulating a screw dislocation in a BCC crystal difficult at the atomic scale? Does someone know? That's true, yes. But that would not be our problem with the atomistic simulation. One process is thermally activated, the other is not. Between the good guys and the bad, the good guys are processes that are not thermally activated, because then they occur on a very small time scale, which can be easily simulated using atomistic simulations. The thermally activated processes, they will depend on their time scale will depend on temperature, but unless you are at very high temperature, the time scale of the thermally activated processes will always be much larger than what you can model with atomistics. And so you cannot use brute force molecular dynamics to model them. Maybe this afternoon, no, not this afternoon, one of the afternoons, we're going to, yeah, it's the third day. We're going to look at the migration of a vacancy. If I ask you, all of you run an MD simulation to look at just one vacancy in a crystal, and you look at when the vacancy moves, I can bet that none of you, depending on the temperature, but there's a good chance that none of you will ever see a dislocation jump, because it has to go above an energy barrier, and that will take a time which very quickly is much longer than what you can do with MD simulations. Why is that? So what's the typical time of a thermally activated process? So the time scale of a thermally activated process there's a mathematical formula that we're going to use. Do you know if it's thermally activated, the typical time? So I have a vacancy that moves from one position to the next. And to do that, the vacancy has to go above an energy barrier here. So that would be the vacancy in its initial position. That would be the vacancy in its final position. And between the two, when the vacancy is exchanging with an atom, the energy goes through an energy barrier. That would be delta E here. That's the energy barrier. If I have an energy barrier delta E, the typical time it will take for the vacancy to move will be, how it will be expressed? Yes, exactly. So it's going to depend on E over kBT, right? So that's Boltzmann constant, the temperature, and then the delta E here. I put an exponential, yes. So if it is time, it's a plus. It's a minus with the frequency. And then if I want to put a characteristic time here, what would I put? It's 1 over a typical vibrational frequency. And what's the typical vibrational frequency? It's called the Debye frequency. And so the Debye frequency, it depends from material to material. Usually what we say is that it's on the order of 10 to the 13 per second. Right, so if you plug in numbers, you say here, for example, you put a half an EV, you put a room temperature, you put 10 to the 13. What you get here is something which is on the order of 2.5 milliseconds, sorry, milliseconds for delta E, which is 0.5 EV, which is the typical barrier for vacancy migration. And then you put KBT, which is 1 over 40 EV. That's the thermal energy at room temperature, etc. So 2.5 milliseconds. We're going to talk about timescales at the end, but this is orders of magnitude longer than what we can do with MD simulations. So we're never going to see it. There are different solutions, and we're going to talk about that on day 4 or something, right? It's not brute force MD. That's the thing. But there are other options. So like you have Monte Carlo that you can use, or you can use accelerated molecular dynamics simulations, but you need to play tricks. You cannot do just a brute force MD simulation for that. Those fast processes, as I said, so typically, surface relaxation, for example, this is usually not thermally activated, and so it's a fast process, and it will occur on the order of nanoseconds. And usually the temperature dependence of these processes is low, so it can be no or linear, or but it will be a small dependence. The thermal activity processes, their time scale anywhere between 1 to 10 milliseconds, seconds, even more, and they have an exponential dependence on temperature that we have talked about. So examples, so atomic vibrations are not thermally activated, and we said they occur on the order of 10 to the 13, 10 to the 12 or 13. The glide of dislocations when there's no resistance of the lattice, and that's the case of FCC metals. The FCC metal does not resist the glide of dislocations, and so the glide of dislocation in FCC is not thermally activated and occurs very fast, even on MD timescales. Then you have all of the displacive phase transformations. So phase transformations that do not require diffusion. They will also propagate at velocities that are very high, and then brittle cracks also. So these are the good guys. Now the bad guys is everything related to atomic diffusion, diffusive phase transformations, the glide of dislocation when there is a resistance due to the lattice. So this is the case of screw dislocations in BCC metals. And ductile cracks also will propagate thermally activated. If you apply a high enough stress, so the velocity if you apply a high enough stress, at some point the dislocation will start to glide fast enough that you can see with MD because it's biased by the stress, but you will be at a stress much higher than in the experiments. You can always, with dislocations or with cracks, you can always play with the applied stress to be close enough to the resistance of the lattice, the pile stress, to see the dislocation moving, but you're not in realistic conditions then. But for vacancies, for example, you cannot really, if you apply a stress, you can change a little bit the diffusion barrier, but not much. And so there, with brute force MD, there's nothing you can do. With climb, so maybe it's too advanced for the others, but just for you, an issue also with climb and dislocations is that if I take a typical simulation cell with one dislocation and I put one vacancy, I will be much higher than the equilibrium concentration of vacancies. I will be super saturated. So even just one dislocation. So even if that dislocation was able to be absorbed, I would overestimate the climb velocity because I'm overestimating the concentration of vacancies. Climb is extremely difficult to simulate even in simple systems at the atomic scale. Sorry, that was probably too involved for most of you, but is it okay? Yeah? And so, yeah, so again, so this we can simulate easily with a laptop workstation, single node calculation. This quickly we need large simulations, or in particular we need advanced simulation methods. These accelerated molecular dynamics that I don't really want to talk about now. Okay, now in terms of energy models, so there are different families, and they are ordered here as a function of their computational cost. So the most accurate calculations we can do, at least in material science, is using density functional theory calculation. Someone mentioned VASP earlier. These are, so when you know how to do the simulation properly, they are extremely, they can give you quantitative predictions about materials properties if you do it right. But they also cost a lot of computing time. Typically, still nowadays in metals, it's difficult to go beyond a few thousand atoms. And just for relaxation simulations, not molecular dynamics. So here you're really limited to very, very small simulation cells. Then for a long time, so this is something which is historical and not really used nowadays. For a long time, we had either this or we had that, which are the semi-empirical potentials. So the embedded atom method potential or the modified embedded atom method potential. I will say a word in 2 slides about them. And now since, I don't know, less than 10 years, in between those two, we have the machine learning potentials that have come up that can be very accurate. They cost much more than the semi-empirical potentials, but much less than the electronic structure calculations. So these are the type of choices for energy models. Together, we are only going, unless you want to do it on your own, but for the tutorials, it's only based on EEM potentials to have fast calculations. In terms of atomistic methods, so the fastest, the ones that we are mostly going to use together, are molecular statics simulations, where we only look at equilibrium configurations. And we're going to also discuss what we call minimum energy path methods. So methods to numerically find what are these energy, how to find the energy barrier, for example, for the migration of a vacancy. These are still relatively fast calculations. This is all in the same category of minimum energy path methods. Then molecular dynamics and Monte Carlo take much more time than molecular statics, just because here you generate a lot of configurations, where here you generate only a few configurations. So they take much more time. All of this is done in classical mechanics. If you want to add quantum effects in the motion of the atoms, not necessarily in the interaction, but in the motion of the atoms, you need to go to path integral molecular dynamics or quantum Monte Carlo, and these are extremely computationally expensive calculations. Right? So things that you can do in a reasonable time is DFT with molecular statics. That can be done. You can do DFT with Monte Carlo or with, so this you can also do. So molecular statics, minimum energy, you can do with DFT. This you can do, but then you have to use really small systems, otherwise the computing time explodes. And this, to my knowledge, is not really doable. Or only on a very, very few atoms, and then you don't use DFT, you use more advanced quantum mechanical descriptions. Machine learning, you can do all of this. I'm not sure if many people have started doing PathMD with machine learning, but probably it has been done. And EEM, you can do everything. This is yeah, so I'm going to discuss it. This is just the introduction. Molecular statics is just when you do energy minimizations, when you only look at equilibrium structures. I will describe it.
That path integral MD, is it something quantum?
It's to account for the delocalization of the atoms. So it's to account for 0-point vibrations as well as tunneling. You use this was invented by Feynman, Richard Feynman, and it's yeah, no, I cannot really go into the details, but this is to include quantum effects in the trajectory of the atoms. So you have quantum mechanics in the interactions. All of this is based on electrons and quantum mechanics. All of this is classical mechanics for the motion of the atoms. These methods also include the fact that the atoms are delocalized. And you can get 0-point energy vibrations using these methods. So what I want to say now is a few words about energy models. First, yeah, I'm an old guy in the field, so I can have a word of wisdom. My word of wisdom is that a potential will always have limitations. There's no perfect potential. The key point here is that when you have a potential, you have to know it. You have to know where it's good, and you have to know where it's bad. And obviously, you should use it only where it's good. So always know the limitations of your potentials. An important distinction, in particular nowadays with the machine learning potentials, is the difference between accuracy and transferability. So a potential is accurate, especially a machine learning potential is accurate when it can well interpolate between the configurations that we have used to train the potential. It is transferable when it can predict new structures that were not in the initial database. So transferability is extrapolation, accuracy is interpolation. And so there are many of the machine learning potentials that are very good at interpolating. They are super bad at extrapolating. The semi-empirical potentials, they are not very good nor not very bad here, but they are not as bad as machine learning potentials. They extrapolate a bit better than the machine learning potentials, but they are not as accurate as they are. And all of this is very, very well discussed in this review paper by Yuri Mishin, which is one of the people who knows how to do very good EEM potentials. And he has moved to machine learning potentials recently, and this is a very interesting paper for all of these aspects. Okay, so traditional semi-empirical potentials. What I want to discuss is different families and then discuss their speed, their transferability, their accuracy, and the typical number of parameters that you have in them. So the first I want to talk is, we already mentioned it, it's Lennard-Jones type potential. So it's pair potentials. So the energy is just the sum over all of the atomic pairs of a function that looks like this, as you have drawn. And it depends only on the relative position of the two atoms. So these are clearly the fastest calculations. So that would be my reference speed. I will call it 1. So the transferability is relatively limited. The accuracy is very limited. In particular, when we look at crystals, they are, because of the pair formalism, there are some relations that are unavoidable, like what we call the Cauchy relation. So with a pair potential, these are elastic constants. For a cubic system, the elastic constant C12 has to be equal to C44. There's no way around it. So there are some limitations even in the elastic properties of the crystal that you're looking at. But there are very few parameters from, say, 2 to 5 parameters. Now, the level above is the EEM. So you keep the pair potential part, and now you add a term here which is not a pair potential. So it starts with a term here that you compute as a sum over, so for each atom, you compute this term as a sum over its neighbors. But then this number here, you put it in a function which is called an embedding function that breaks the pairwise structure of the potential. This term here is supposed to, initially in the fathers of the method, this term here was added to represent the electronic contributions, the electron contribution to the energy. And this was the interaction between the anions in the metal, right? So that gave a lot of flexibility to add this second term. It's almost as fast as a pair potential. It's just twice slower, because computing this term is about the same time as computing that term, so it's 1/2. The transferability is a bit better than the pair potentials, reasonable. the accuracy is also reasonable, although these potentials have a hard time representing core structures, for example, or low symmetry phases. This is very difficult, or even stacking faults are difficult to represent with these potentials. And the number of parameters is anywhere between 10 and, say, 20 parameters. They are close, yes. In magnitude, they are close. Now, initially, so this term, there was some physics in this term from so the fathers of the method, fathers and mothers of the method, had some physical expressions for these functions. Nowadays, you just take polynomials and you adjust everything. You forget about the physics. You just have a pair term and a many-body or a non-pair term here, and that's it. But yeah, roughly they are of the same magnitude. And then, what would be the next step? What would you add? Yeah, the modified EEM. And so what's the difference between EEM and modified EEM? What is added in the modified EEM compared to the EEM? Angular interactions, yeah, because this is still only a function of the relative distance between atoms, and that's why it has a hard time reproducing the low symmetry phases. If you want to have low symmetry phases, then you need to add angular terms. So you still have the EEM, and now you had a term here that will depend on the angles between the neighbors. This one is about 10 times slower than the pair potential. Okay, I will be a bit nasty about MEM. For me, in my experience, maybe I'm wrong and maybe you will disagree, and I will respect that. I've never found much progress using MEM compared to EEM. The transferability is a bit better, but not that much better. The accuracy is not much better either, except for some specific low phase systems, not for metals. The number of parameters is much better, is much larger, much more work to fit these potentials. So anyway, so for me, my go-to formalism is EEM potential. I think they are the best compromise in the different types of potential. If I have an EEM potential, for example, so this is a very specific case, but I said that the simple cubic crystal is not stable unless it is polonium. The reason is that with only a potential which is only based on distances, that thing will always be unstable with respect to shear. If you want to stabilize it, you have to stabilize these angles. And this is done through this term here. Okay? So the idea with these potentials is that you start with mathematical functions for all of the different terms here, and they contain parameters, and then you optimize these parameters based on relatively, usually because you don't have that many parameters here, the database is not very big, usually less than 100 configurations. That nowadays they are mostly coming from density functional theory calculations. Back in the days, they were also using experimental values. So you adjust the parameters of these functions to reproduce as best as you can some configurations, and then you live with that potential. Yeah, so the data, initially, they were using experimental data. So they would use experimental cohesive energy, lattice parameter, elastic constants. And when you have a Lenage's potential with only 2 to 5 parameters, that's enough. You can use only experimental, or experimental data is enough. With 20 or 40, or in particular nowadays, what we like to use is DFT calculations. So you use DFT to get the relaxed structure and energy of different phases, and you use that to fit the potential. Also, liquid structures. So what has been shown maybe 20 years ago is that if you add liquid structures to your database, that will very much improve the transferability of the potential. And so you fit the energy and even the forces of ordered and disordered structures that you have relaxed with DFT. So that's typically, there are most potentials will be good for either one or the other. It's very rare that you would have one potential that is good for both. So that's part of the wisdom thing where you have to know, before, if you have a titanium potential and you want to do simulations in HCP, first you need to check what are the properties that your system predicts for HCP. For example, the stacking faults or the elastic constants and so on. If you want to use the same potential for BCC, first you check what does the potential predict for the BCC phase, because it might be completely off. And that you cannot know beforehand. Yeah. And that's true also for machine learning potentials, by the way. Oh, so DFT, so the guy or the woman who invented the word ab initio is a genius, because there's nothing less ab initio. No, there are things less ab initio than DFT, but DFT is by no way ab initio in the sense parameter free. DFT is full of parameters, full of choices, and that's what I was saying. When you know how to do DFT properly, it can give you quantitative predictions, but it can also give you crap if you don't know what you're doing. And that's one of the issues with, VASP nowadays. You buy VASP, you download it, and then you run it, and then you say, oh, I'm going to write a paper. If you don't know what you're doing, you can really, really say very wrong things. You have to be very careful with DFT also. In DFT, the systems that you will use will always be very small, right? It's going to be a few hundred atoms at best. So for example, if you are interested in dislocations, like I am, with DFT, you will never be able to simulate a long dislocation, because that would require way too many atoms. So you only look at a very short dislocation perpendicular to the cell. So with DFT, if you know how to do it properly, you spend the time you need, you can be quantitative but with a very short dislocation. If you want to look at what is happening to a long dislocation, you will not be able to do it with DFT. So then that's where you fit a potential with the DFT, and you use it with MD to be able to look at a long dislocation. So there are some problems that you can answer with just DFT, and that's perfect. But then some others you need bigger cells, or you need to do dynamics. And with DFT, you can do ab initio molecular dynamics, but that's extremely computationally expensive, and so you will do it only with very small systems. Typically, you cannot do it with dislocations, for example. So this is, in our community, this is a very famous paper where Machine proposed EEM potentials for FCC metals, and they are still considered the holy grail of EEM potentials for metals. So first, the formalism. You see, so where are they? Yeah, so he gives functional forms for the different terms of the potential. So you have mathematical forms. So you have, for example, here, the rho that you had, the rho Rj, he proposes to use this mathematical form with the sum of two exponentials to represent the electronic density, and you have parameters. A, beta 1, R naught, beta 2, R naught. And this is just to stop the function properly at some distance here. Here you have a functional form. Again, this is a difference between two exponentials for the pair potential. And that gives you more parameters. And then I guess, what else we have? And then we have the embedding function, the F function here. Again, there's some mathematics. He proposes to use some mathematical form. And then so these are the parameters. There should be a table. Yes. So these are some of the parameters he used. Wait a minute. No, actually, I'm not sure which one he used for the training and which one he predicts. But you see the idea. Yeah, no, I'm not sure which one he used. That might not be the best example. So I can find one for this afternoon if you want. There may be a better example. But typically, the properties that were added are defect properties. So you have the properties of vacancies and interstitials. This is something that you cannot really reproduce with Lennard-Jones potentials, and that you can with DFT. So you have that, and there should be surface, and then surface energies. same thing. You're with the Lennard-Jones, you're very limited in reproducing surface energies, and so these were. I'm not sure which one was used in the training, but that's the idea. And then there will be energies of different phases. Really, especially nowadays, it's machine learning potentials. As I said, I could have come and spend the whole week talking about machine learning potentials. What I want to say is that I don't want to go into the details, and it's too late now. But what I want to say is that the philosophy of machine learning potentials is very different from potentials. So from potentials, as we said, we take a mathematical form with parameters. We fit the parameters once and for all, and then we use the potential, and that's it. With machine learning potentials, the objective is to have a database of configurations, and then when we give a new atomic configuration, we want to interpolate that atomic configuration among those of the database. It's always, we do interpolations. We interpolate and interpolate and interpolate. With the potentials, we don't interpolate. We just see what is the mathematical value that the potential gives. With machine learning potentials, we interpolate inside the database. That's really the idea. Now, to do the interpolation, we need a way to measure what is the distance between the configuration I have and my database. And so that's done through what we call descriptors. So something that would tell us what's the distance between the configurations, and then some kernel function that is used to do the interpolation. Again, I don't want to go into the details, but that's basically the idea. With machine learning potentials, we start with an atomic configuration. We find a way to measure its distance with respect to the other configurations of the database. Then we do a regression, which is the interpolation, and that gives us the energy. And we do that at every step. This is too. So really, I just want to talk about the philosophy. The philosophy is, with machine learning potentials, we do interpolations, whereas here we really do predictions from a set of mathematical functions. Now machine learning potentials are really great in terms of accuracy. They are really much better than EM potentials. But there are two issues with machine learning potentials that I want you to keep in mind. The first one is the computational cost. So this is it's a very interesting paper here where they have compared many different types of machine learning potentials. I don't want to necessarily get into the details. So these are called the gap potentials. These are historically some of the first potentials, so Gaussian approximation potentials. These are more recent potentials, moment tensor potential. These are neural network potentials, and then the snap potential that are just a variation. And so here you have, this is basically the accuracy of the potential as a function of its computational cost. Gap potentials are really great because they can be very accurate, but they are extremely computationally expensive. And nowadays, they are no longer really, some people still use gap potentials, but less and less because they are way too expensive. If you look at the moment tensor potentials, they can be roughly as accurate as gap, but they take 20 to 30 times less. So they are much better. And then if you want to be faster and faster, then you have to pay the price in terms of accuracy. And the other potentials are about the same. So MTP are very much used. NNP, so neural network potentials, they have made a lot of progress. And probably, so these data are not, I don't think they are completely accurate. I think now you can be here actually with NNP potentials nowadays. They have really made a difference. The EM potentials on that graph, they are here. So EM potentials in terms of time scale, they're really on the left side of the graph. But in terms of accuracy, they're not so good, obviously. So they're basically, you keep this line, you keep up, and then you end up at the EM potentials. Yes, yeah. And outside of the training database. On the configuration you have used to fit the potentials, they are very good, but then outside, this is the typical error that you have. Some hundreds of millieV per atom. And the other issue, as I said earlier, is the transferability. So this is taken from Yuri Mishin. So I had a discussion some years ago with Yuri Mishin, and basically what he told me, and this is what is at the core of his review paper, is that a traditional potential is never really very good nor really very bad. So even in the training database, you will not be exactly on the points. But then if you go outside the training database and you do extrapolations, it will not be perfect, but it will not be very far off. Machine learning potentials, in particular the early versions of neural network potentials, they were extremely good on the database, but they can really give you crap outside of the database. The idea of Yuri Mishin is to have what he calls physically informed machine learning potentials. So basically, he starts with the shape of an empirical potential, like a Lennard-Jones potential. But now what he does is he does machine learning on the parameters of the potential. So now every atom has its own group of parameters. And these parameters are obtained, for example, using a neural network potential through training. And what he says is that what is good is that because you keep a physical form here, it will never be that bad when you do extrapolation. But with the multiplication of parameters here, you can be extremely accurate also at the same time. Again, so I won't go into much more details. This is just the philosophy of these physically informed machine potentials. This is quickly what I wanted to say about potentials. Yes, go ahead. For me, extrapolation is if you try to predict the properties of configurations that are not in the training database. So for example, you train your potential only on FCC structures, and then you want to look at what your potential says about BCC structure. This is extrapolation. And our everyday experience shows that with pair potential, BCC will not be exact, but it will not be completely bad. You take a machine learning potential and it will predict that the BCC phase, for example, is completely unstable, whereas we know it is metastable, for example. That's also, there's a choice in the descriptors, and there are some descriptors better than others. There's a lot of progress nowadays. I mean, a lot of people are testing and proposing new descriptors. It's clearly moving fast. Another issue with machine learning potentials is that, I mean, once you have the potential, you can run big simulations, but you spend a lot of time initially doing a lot of DFT calculations to build your database. So there's a huge price not huge, but there's a big price to pay at the beginning to build a database. Then it's relatively fast, but you have to build this database. Although again, in that case, there are also a lot of progress, which is being done. Very interesting. It's called active learning. What you do, it's very, you start by making, you do a small database of a few tens of configurations, not more, and you train several potentials on that small database. Then you run MD, and you look at whether the trajectories predicted by MD with the different potentials are close or if they diverge. If they are close, it means that actually what you're looking at is well predicted by your potential. I mean, you have some confidence. Then even if you change a bit the parameters, your potentials are predicting all the same, so it should be okay. If they start to diverge, it means that you are going away from your database, and you need to add more configurations. You stop the MD, you take a configuration, you relax it with DFT, you put it in a database, and you retrain your system, and then you run again. And so that the idea is that you want to add DFT calculations only when you need them. And so your database will grow, but slowly, and this is extremely efficient to build potentials. We've done that with Zirconia, for example. It's really extremely efficient. Yes? Okay, so it's a bit late, but I just want to say a few words about atomistic methods so that you're not going to be completely lost this afternoon at the beginning of the tutorial, okay? So bear with me, it's going to be fast. I will not go into any technical details. So the first thing I want to talk about are boundary conditions. So the best by far boundary conditions you can use is periodic boundary conditions. So another word of wisdom is always use periodic boundary conditions when you can. So the idea, I hope is clear for everyone. So the idea is that this would be the simulation cell that I have in my code. Now I embed this configuration with replicas of itself all around it. So if I have a blue atom I here and a J atom I here, I will find the same atoms by periodicity here, here, all around. And when I want to look at the distance between atom I and J, actually I have the choice between looking at the pair which is inside the cell or looking at the pair with the periodic image in a neighboring cell. And the idea in the calculations, what we call the minimum image convention, is that we always take the closest image, or we take the distance which is the smallest between the two to compute the distance between these two atoms. So this is as if when I'm looking at the interaction between this atom and that atom, actually I'm looking at the interaction of this atom with its periodic image here, or equivalently, the interaction of the periodic image here with that atom. Right? So what is very nice with these periodic boundary conditions is that there's no free surfaces, or there's no need to block atoms on the sides, and that minimizes size effects. I'm not sure, I don't think there's any mathematical proof of that, but in practice, the size effects are always smaller if we use periodic boundary conditions. So use them if you can. Just to say that in an MD code, the main function is what I call here the energy function. So this energy function, it's a function that takes the energy model, whether an EEM, MEEM, machine learning potential. It takes the atomic configuration, it takes the boundary conditions, and then it computes. So the basic knowledge, the basic value that it gives you is the energy of the configuration. But then also by taking the gradient of that energy, it gives you the forces on the atoms. And by taking the moments, so the forces times the distances, it also gives you the stress tensor. Right? So all the atomistic methods, they are based on these three information about the atomic configuration. And that's all what we need. Its energy, its forces, and its stress tensor. And in most cases, like the EEM potential I showed before, all is analytical. And even with machine learning potentials, the gradients and the tensors are all analytical. Say more about the size effect? Actually, I think this afternoon I asked you to compute with the formation energy of a vacancy in different cell sizes, I think. You will see the size effect there. You see that, with MD, we always try to use small cells. And if we do that, then a vacancy in the main cell will interact with its periodic images. And so if you compute the formation energy of that vacancy in that cell or in a cell twice bigger, you don't get the same number. So there will be an evolution of the energy as a function of the size of the cell. In practice, if I do the same calculation with free surfaces, I can do the same. I can put free surfaces and I look at the energy in bigger and bigger cells. I will also have a size effect. In practice, in most cases, it will take longer to converge. It will converge to the same value, but it will take longer. But it's more of empirical. I don't have any mathematical. Actually, there's not one single answer to that. The size that you have to take depends on the system you are looking at, depends on the process you are looking at. For example, in practice, for dislocations, if you want it to be exact, it should be infinite. With vacancies, it can be relatively small because the interactions between vacancies dies as 1 over r squared, so it dies relatively quickly. Dislocations that interact with a 1 over r interaction would take an infinite cell to have no size effect. Okay, so there was a question about molecular statics. So this is the idea. So molecular statics, the idea is just to minimize the energy of a system with respect to the atomic positions. To find, so a system that has a minimum energy has 0 forces, since the forces are the gradient. If E is minimum, the gradients are 0, so there are 0 forces on the atoms. So that's an equilibrium configuration. And molecular statics just means I'm going to compute what is the equilibrium configuration of my system. And maybe worse, the algorithms that we use to minimize the energy. So there are two main, for example, in lamps, there are two main algorithms. The one which is called the conjugate gradient algorithm and the other one fire. They will give you only the closest energy minimum from your initial configuration. So it means that if I draw here, for example, this would be, schematically, this would be the position of the atoms, and this would be the energy. And so if my energy looks something like this, if I start from here, so this is my initial configuration. These algorithms, what they will do is they will minimize the system up to here. And they will not know, for example, that there's a big minimum nearby. It will give you the first metastable state, or the closest metastable state to your initial configuration, not more. So same thing, you have to be careful. Ideally, what you should do is start from different, if you want to have a real minimum, you have to start from different initial configurations, and you see if for different initial configurations, you converge to the same minimum or to different minima. Very few people do it, but that's what you should do. So yeah, the conjugate gradient method was designed so that if the minimum that I have here is perfectly quadratic, then in that quadratic, so it would be in 2D, right? If I have a 2D quadratic well, wherever I start in that quadratic well, in 2 steps, I will be exactly at the minimum. So that's how the conjugate gradient was designed. The thing is, the energy minima are never exactly quadratic, so it will take more than 2 steps to converge. And at least the way it's coded in lamps, very often actually it can even become unstable, or it cannot, it stops. Many times the conjugate gradient will stop before it has found the minimum. So we can also use the fire, which is, yeah, it's a bit late to go into these details, but it's called, it's a quench dynamics algorithm. Now we'll talk about that later. It's another algorithm, which is more stable than the conjugate gradient. Anyway, so words of wisdom. So algorithms are iterative, and so they are iterative, and very often the evolution during the energy minimization, it looks like an MD trajectory. It looks like the atoms are rearranging because at every step, at every iteration, they move a little. We should always keep in mind that this is not actual dynamics, right? Just the system which is moving towards an energy minimum. So we have to be careful with that. Many examples in the literature of people mix temporal evolution with energy minimizations. And as I said, they give you only the closest minimum, as I said. So a static simulation is when you go only to one minimum, right? Now you can do what we call quasi-static simulations, which is, for example, you go from minima to minima. So for example, I take a system and I do an initial compression. So I change its size to this. So I compress it, and then I do an energy minimization. So here I start with a minimum. So I have a first configuration, R0. This is my first configuration. I squeeze a bit, I re-relax. That gives me a second configuration. I squeeze a bit more, and I re-relax again. That gives me a third configuration, and et cetera, et cetera, et cetera. So a quasi-static simulation, it's when you change the boundary conditions in small increments, and you do an energy minimization in between each increment. So you go from minimum energy configurations to minimum energy configurations, but each time by changing a little bit the boundary conditions. It's because it's very fast compared to MD simulation, much faster than MD simulations. But because you go from equilibrium configurations to equilibrium configurations, what don't you have? There's one thing you don't have in these simulations. If you go from minima to minima, you don't have temperature. You have zero temperature. Since you go from minima to minima, you have zero temperature. But since you go from minima to minima, so actually physically, it's as if you were doing an extremely slow deformation at zero temperature. So quasi-static simulation, I think I wrote it somewhere. It's the limit of 0 strain rate, but also 0 temperature. So it's a weird limit, but it can be very useful, in particular, so in metals, but also a lot in crystalline metals, but also a lot in glasses, for example. Many of the studies of the mechanics of glasses are done using quasi-static simulations. 0 strain rate, 0 temperature. If you fix the boundary conditions, it cannot go back here. So you start with these boundary conditions, you compress, and then you hold this fix, and you re-relax. Then it cannot go back here. And you continue like this. At least in one direction. So for example, in this example, you have to keep this height here fixed, but you can relax, for example, perpendicularly. It does not need to. I mean, for a crystal, for example, the volume will not be conserved because of Poisson ratio, right? So it will expand, but not necessarily at the volume, at the initial volume, depending on the Poisson ratio of your system, right? So you have to you have to constrain one of the dimensions. So it can be either this, or if you do shear, you apply a shear by step, and then you minimize everything inside. You can relax the volume if you want, but you have to keep the shear constant. Okay, I won't go into this. Okay, we don't need molecular dynamics, so I'm gonna go. Actually, we can stop here because this is all dynamics. So we can talk about that later on. I think it's better because I can feel that everybody's tired, and me included. So some more words of wisdom before we go for lunch. So choose carefully and know the limitations of your interatomic potential. I think I've insisted enough on that. Always use periodic boundary conditions when you can, and always try to simplify your problems as much as possible to have the smallest simulation cell. I'm not a big fan of the huge simulation I showed before by Vassily Bulatov. I have a lot of respect for Vassily Bulatov, but these huge brute force simulations I don't know. That's not my way of doing science. Now, keep in mind, so all potentials have their limits, right? There will always, even the best machine learning potential, it will be crap somewhere. This we haven't really talked about, but MD simulations at finite temperature will always underestimate thermal activity processes, but we'll talk about that later. And this is more a philosophy of research, is seek the unexpected. And we're gonna, this week will not be enough, but always try to go beyond what you already know or what experiments have already told you. But that's beyond what I wanted to say this morning. Okay, I'm done for now. I was initially supposed to introduce what we're going to do this afternoon, but I prefer to do it this afternoon. Okay, so we stop here? Great.